Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives. If you haven't already, make sure to check out some of my previous videos. They're linked in the corner or below, whichever you want to check. I have the playlist right there. Otherwise, today specifically we're talking about continuity and how we can work with derivatives. So let's go ahead and dive into it. So we're starting off with a definition here. We have if a function f is differentiable at a value a, meaning we can find its derivative, then f is continuous at that same value. So question, what does this mean? Let's go ahead and look at an example here. In the red, we have f of x equals x cubed plus 1. And our first derivative is going to be 3x squared. And really what we're looking at is if we can find the derivative at every single value. So here I can plug in any value of x and I get an output, right? I get a value. This means that the function f of x equals x cubed plus 1 is continuous for all values of x. And thus, f of x is differentiable for all x values. AKA, there are no illegal values in the derivative. So we have another theorem. We get a bit more interesting here. If a function f is not continuous at a value a, then immediately f is not going to be differentiable at a. So if we took the derivative and we plugged in a, we would get some kind of illegal value. So let's go ahead and take a look at this. We have f of x equals x minus 2 when x is less than 0, and x squared when x is greater than or equal to 0. We're going to go ahead and graph both sides of this. So first, let's graph x minus 2. So if I plug in 0, I get negative 2, but I have a hole there because I don't actually equal 0. And from there, when I plug in values, negative 1 minus 2 is negative 3, negative 2, it gives me negative 4, and I have a function just like this. Alrighty, so now let's go ahead and graph the other side. So when x is greater than or equal to 0, we have x squared. When I plug this in, I get 0, 0 is a point, and I fill in that hole because I actually equal 0. When I plug in 1, I get a value of 1. When I plug in 2, I get a value of 4. So I'm just going to graph it like that. And here I can see a discontinuity. So if I look here, I'm jumping from a value of negative 2 up to a value of 0. This is what we call a jump discontinuity. If we remember the definition of continuous, the easy definition is where I never lift my pencil up. In this case, I do have to lift my pencil because I have to jump from negative 2 to 0. So immediately, I know this is not going to be differentiable at 0. But we're going to go ahead and look at the derivative anyways. So here, f prime x, I can take the derivative of the corresponding sides. So first, we can take the derivative of x minus 2, and that's just going to be 1. And the derivative of x squared is going to be 2x. So if I were to plug in the x equals 0 right here, if I plugged in x equals 0, I get an output of 1 because it's always just going to be 1. Now on this other part, if I plug in x equals 0, my derivative is just going to be 2 times 0, which is equal to 0. Notice here I have two different derivatives at x equals 0. Now it might be a bit confusing because this is the only part where we're including 0. But we want to look on the entire number line to see if f of x is continuous. It is not continuous, therefore it's not differentiable. We want the derivatives to be the same on either side of that point. And it's not going to be the same. We're going to have a derivative of 1 and a derivative of 0. So in this case, f of x is not continuous at the value x equals 0. Therefore, f of x is not differentiable at the value x equals 0. So let's drink some tea. Okay, so we are going to look at an interesting example. We have the absolute value of x, and I'm going to go ahead and rewrite it because right now we're not sure how to find the derivative of the absolute value of x. So I'm going to split this into two separate functions. Let's go ahead and look when x is less than 0. We have a negative linear function of negative x. Now when x is greater than 0 on the right-hand side of our graph, we're going to have a positive x. It's just a linear function, right? So now using this, I can go ahead and find the two different derivatives, and we can take the derivatives in pieces. So the derivative of negative x is going to be negative 1, which is graphed right here. And the derivative of positive x is just positive 1, which is also graphed right here. So this is what I was talking about when our derivatives, look at, they jump up from negative 1 up to positive 1. So that means it's not differentiable at the point x equals 0. But if we look at our function is still continuous. I never have to lift my pencil. I have that they're approaching the same value from both sides. So our function f of x equals absolute value of x is continuous at the value x equals 0. However, f of x is not differentiable at the value x equals 0. So sometimes we can have a continuous function, but it's not differentiable at a value. So question, when is a function not differentiable? It might be continuous, but it might not be differentiable, and we are going to look at some examples. So our first example is just like the absolute value of x. It's when we have a cusp, or some people call this a corner, whatever you prefer to call it. It's when we have a super sharp edge. And that's because the tangent lines are changing at such a rapid rate, we can't even take it into account. So what I mean by that is let's go ahead and graph the tangent line right here. It's going to be the line that just passes through it, just like that. So I would say this is a negative tangent line because it has a negative slope. Now, if I move over to the other side and I graph this tangent line, I notice that here I have a positive slope, right? How do we switch from negative to positive so quickly? Because what they're doing is they're getting steeper, right? If I go even closer, they're getting way more steep. So that's why we call it not differentiable, because those tangent lines change so rapidly we can't even take it into account. So that is a cusp or corner. Here, this is a jump discontinuity, just like we talked about in the first example. The function itself is not continuous, therefore derivative is not going to exist right there. So this would not be differentiable at x is equal to a, right here on that value. Another way we can see this happening is when we have a vertical tangent line. So if I were to draw a tangent line right here at A, it would be vertical, which means we have a slope of 0. And this is illegal, not allowed. We will see an example of that later on. Finally, we also have vertical asymptotes. So this is another type of discontinuity where we're not able to connect the two pieces together. So we have a function on the left side, a function on the right side, but it's not defined at x is equal to a. So when the function is not defined, the derivative is also not going to be defined. So let's go ahead and try some examples. First, we have f of x equals 1 over x minus 2. So we need to find where f of x is discontinuous. And we're going to do that by looking for illegal values. So if I remember, I cannot divide by 0. Therefore, my denominator cannot be equal to 0. So I'm going to go ahead and find that illegal value, and I'm going to do that by setting the denominator equal to 0. Adding 2 to both sides, I get x is equal to 2, and this is where my function is not going to be continuous. So we're going to do a proof of this, finding the derivative and plugging in that value. We are going to find the derivative in two ways. So first, I'm going to go ahead and use quotient rule, and I'm going to set that up. My numerator, f of x, is equal to 1. And my denominator is going to be g of x, and I'm going to set that equal to x minus 2. Let's go ahead and find our derivatives. So the derivative of 1 is just going to be 0, and the derivative of x minus 2 is equal to 1. When I'm finding my actual derivative of the function, I start from the bottom and work my way to the top. So I get 0 times x minus 2. Now I subtract from the top going to the bottom, so that will be 1 times 1. And all of this is divided by the denominator, x minus 2 squared. So this whole term is multiplied by 0, which means it just goes away. And in the numerator, I'm left with a negative 1. And in the denominator, I'm left with x minus 2 quantity squared. I want to show us another way that we can do this. What I can do is rewrite that with a negative exponent. So x minus 2 to the negative 1. And actually what we can use here is chain rule. So I have my inside, which is x minus 2, and my g of u is the outside. So it's the inside to the power of negative 1. If I find my first derivative of u, I just get a value of 1, and my g prime of u is going to be negative 1 u to the negative 2. I just use power rule. So when we're finding our derivative, f prime of x is equal to u prime times g prime of u. So negative 1. I'm going to plug u back in, so I get x minus 2 to the negative 2. Rewriting this, I get a negative 1 in the numerator, and since I have a negative exponent, I can just drop that down. And I get the same value. So let me zoom out. You can either do this with the quotient rule, or you can do it with the chain rule. Whatever your heart desires, just go with it. So Remember, we're trying to show that this is not differentiable, which means I want to plug in that value of 2. When I do that, I get negative 1 over 2 minus 2 squared. And here we can see our issue. I get negative 1 over 0, which this is indeed illegal. Or the real terms, it's not defined. So that means we have a vertical asymptote at x equals 2. Therefore, f prime x is not differentiable at x equals 2. Okay, let's go ahead and see another example here. We have a piecewise function, and we're going to go ahead and draw it in. So we have x squared when x is less than 0. So I have a whole at x equals 0. When I plug in negative 1, I get positive 1. And I have a function that, oh, that was terrible. I'm sorry. Good enough. We have a function that goes up like that. So now, when x is greater than or equal to 0, I have a function square root of x. So now I get to fill in that hole. When I plug in 1, I get 1. If I go all the way out to 4, I get 2. I'll go ahead and fill that in. That was a little better. Okay, so let's look at our drawing. I can see here I have a cusp, right? So we have a cusp, therefore something's going to be a little funky. And this is going to be at x equals 0. So right now that's the only issue I see, so I think it's not differentiable at x equals 0. Let's go ahead and do our proof. So we want to evaluate f prime x at x is equal to 0, and I'm going to do that by taking the derivative. So if we take the derivative of x squared, we get 2x. And now let's go ahead and take the derivative of the square root of x. Remember, the square root of x can be rewritten to have a power of 1/2, which means we can go ahead and apply power rule. So I get 1/2 x, 1 minus 1/2 is negative 1/2. I can rewrite that as 1 over 2 times the square root of x. So filling that in, I get 1 over 2 times the square root of x. Now we want to go ahead and evaluate that derivative. So let's go ahead and look at where our issue is going to be, and it's going to be right here. Because if we plug in a value of 0, what's going to happen? We get 1 over 2 times the square root of 0, which is 1 over 0. This is super illegal, or in real terms, it's totally undefined. And that right there tells you that it's not going to exist. But if we look at our other value, we get 2 times 0, which is equal to 0. So already we're getting two different values because we have a real number and a legal value. So let's go ahead and fill this in. F of x, it is continuous at x equals 0. I know it's continuous because I don't need to lift my pencil in order to draw out my function. There is a cusp, but it is still continuous. And f of x is not differentiable at the value x equals 0. So here's another example of when our function is continuous, but our derivative does not exist. Well, that's all I have for us today. If you enjoyed this video, please leave a thumbs up and comment other topics or problems you'd like to see done. Thanks for watching.